Hello friends, Eli Hibbett here with the Pwn Your Homework Physics Series podcast. If you're looking to prepare, review, or gain an added edge or point of view about topics in physics, then look no further. Tune in each week to unlock your understanding of the physical world surrounding us. And now let's dive right in. Alright, let's get this ball rolling. How's everybody feeling today? Hopefully fantastic. Hopefully you're doing some really good work, learning about physics, getting everything going. And you're tuning into this because you are ready to learn more, to prepare, to get ahead. I am your humble host, Eli Hibbett. We are on iTunes. We are on iTunes now. Check it out. Search Pwn Your Homework. You'll find me there. Finally got all that stuff straightened out with the guys at Apple, and I am pumped. I mean, I've been listening to podcasts for a while now, and just search in iTunes and see yourself in there is just the best feeling. So if you're thinking about it, make a podcast. I highly recommend it. And yeah, so enough with the frivolities. Let's get into it. Real quick. So it looks like there's a 24-hour delay between when I can post my podcast and when it goes live on iTunes. So if you can't stand it and you have to have it immediately when it comes out, go to pwnyourhw.blogspot.com, and there it goes live as soon as I upload it. And those are all the show notes, so you should probably be going there anyway. And for each episode, I put up some videos, I put up some little things that I'm mentioning here and there, some links to some apps, anything that I think might be useful to help you on your journey. Also, go to 2718productions.com. I will also have resources there that will keep you inspired and fired up to learn about physics and science. So, in keeping with that, let's start off with a quote to get everybody fired up. This quote is from Lawrence M. Krauss, and it's not exactly related to what we're going to be talking about today, but I love this idea. It was like one of the first things I heard about that it gives you a good feeling about what you can find out when you start looking at things objectively, and how science, the stuff that is actually in our universe, is so much more interesting than fiction. I don't know why you'd read fiction when you can learn about what's going on in real life. It's unbelievable. So without further ado, let's get into it. And I read, quote, "Every atom in your body came from a star that exploded, and the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about. You are all stardust. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution and for life, weren't created at the beginning of time." Let that sink in for a second. Carl Sagan, again, I'll gush about Carl a little bit. Not Carl, yeah, I'm on a first name basis with Carl. He kind of was like the first popular guy to throw that idea out about how the calcium in your teeth came from stardust, and that all these atoms, the heavy atoms, had to be made in a big furnace to get that many protons stuck together. And this quote, I felt like embodied it a little better about how, I mean, even the atoms in different parts of your body were generated in different stars and somehow made it here. I mean, that is one heck of a journey. And if that doesn't get you fired up, talk about that around the dinner table, I don't know what will. But, okay, so today we are going to be going over units of measure. And if you're a science-minded individual, the base idea of what you're trying to get at is the facts, the truth. What do we know about? And really the only things we know about are things that we can experience or measure. And so we try to measure things as precisely as we can. And in this day and age, we've gotten really good at it. And so the idea is to sort of minimize the uncertainty. I mean, you look at a fish and you say, oh, it's a foot long. And how do you know? I mean, you're just kind of eyeballing it. And once you get the tape measure out, then you know exactly how long it is. And you're not really relying on somebody's ability to guesstimate. And what you're doing is trying to take your uncertainty, or how good a measurement you can take, and make it as small as possible. You want to minimize the amount of error that you have. And with something like measuring a fish, or, you know, getting on the scale in the morning, doesn't really matter too much. But when you're doing very precise calculations and precise science, that error needs to be as small as possible. And maybe I'll have what my friend Dr. Neptune back one time. We used to have terrible long nights calculating uncertainty of measurements, because there's a very specific, difficult process to calculate it. So each measurement that you take, you have to add up and square it, and it becomes so frustrating, because you're looking at your measurement and you're like, oh man, it's just not quite there. I wish I could get it a little better, because this is going to kill me. It's going to make me look my uncertainty is going to be so big. I'm going to look so stupid when I try to present this to someone. And so that's kind of the basis for what units of measure are. Science kind of divides itself into two different topics, especially physics, and that is the difference between data and theory. So data is what you see around you. You look, you run the experiment, you check it out, you say, this is what we found, this is what we saw. And then the theory is like the pure version of it. You know, you sort of try to streamline everything into some equations to say, this is how these relationships work. And going between data and theory is what really keeps both sides honest. You look, and the data really has to be the driver. The theory, you can come up with whatever you want, but if it doesn't match up with the data, then you know that it's garbage, and you got to go back and either find out what you missed, what you didn't measure properly, and remeasure it and make sure it coincides with the theory, or you know that your theory's not right and you have to make some modifications. And Einstein had a really great quote about this, and he said that if the facts don't fit the theory, we'll change the facts. And it's kind of, you know, sort of sarcastic way of talking about how, as scientists, you kind of let your pride cloud the facts, and you sort of get so into your theory, and you want it to be right, and then when it doesn't, it's very frustrating when the theory doesn't match up with data. And so sometimes you want to just kind of say, okay, you didn't measure it right, and you kind of point and say the data is garbage. But usually that's not the case. But as an aspiring, budding young physicist, you really have to get good at how you measure things. And it's very, very, very important. And maybe we'll do a little bit about sig figs, like significant figures. And that sort of precision can wildly affect your answer. So the basic questions that you're asking are how much. It's basically just quantifying everything. How much do you have? How much temperature? How much time? How long? How far is this away? How wide is it? How long is it? How heavy is it? How much energy does it have? How much voltage is there? How much volume? And so back in the day, they used to have this unit called the cubit. And this is in the Bible. I mean, they're talking about building something that's cubits long. And the distance of a cubit was generally accepted to be the distance from your elbow to your wrist. Something like that. So, I mean, when you start thinking about it, you're like, gee, I mean, it's different for everybody. And, you know, they sort of, you know, primitively, you start thinking about how that may be just about the same for everyone. But when you start seeing people of all shapes and sizes, that's not really a good unit. And so we started standardizing, and there was this conference in France, and they decided to come up with some standardized units. I mean, even in like medieval times in England, there was non-standard. There was no definition of what a foot was, or you know what an ounce was. You just sort of, when you went from town to town, people had different measurements, and so, you know, how can you sit there and say, you know, F equals ma if none of those things are standardized? If m is not the same, if m for mass, you know, F force equals mass times acceleration. If none of those units are the same, if you can't measure things properly, those relationships don't even make any sense. And kind of one of the cool things, the way that this started, I was listening to this really interesting book. Maybe I'll link that up in the show notes. I have to think of the title of it. I'll work that in later. Place title here. Little post-production editing here, guys. The name of that book was Money, an Unauthorized Biography by Felix Martin. It's a riveting read. Check it out, guys. All right. Anyway, back to the show. It really came from accounting. People were very accounting and money, and the whole monetary system is just a way of saying how much and measuring how much of an item you have, and then what that worth is to humanity. And what they came up with in France was this SI units, or System International. And they said, okay, these 7 fundamental units, here's the definition of them. We're going to define them, and they're the same everywhere, and that way everybody's on the same page or talking the same language. And they are, I'll just rattle them off here real quick for you. Temperature is Kelvin, named after Lord Kelvin. Time is the second. I think everybody's familiar with the second. Distance is the meter, which we now have a very nice definition of. Mass is the kilogram, the only unit that has a prefix, kilo, in front of it. Luminous intensity is the candela. The amount of a substance is the mole, MOL. And electric current is the ampere. And they thought from this, we should be able to derive everything else. Everything else will be what is known as a derived unit. And so, force is measured in what we call the Newton, named after Isaac Newton, of course. And this is known as a derived unit. And so what a Newton is actually equal to a kilogram times a meter per second squared. And that falls right out of F equals ma. If you look at force equals mass, kilogram, times acceleration, which we know is measured meters per second squared, you see exactly how that Newton comes together. And that you can, instead of anywhere you're writing in, you can write kilogram times meter per second squared. And that is really important, because then, next you have work, FD. Maybe you'll find this out as you're going through. Force times distance. So you have force, Newton, times distance, meter. And you have kilogram times meter squared per second squared. And so when you're writing equations, not only do the numbers have to even out, but the units have to even out. And this is key. This is critical. And a lot of times, what you can do when you're looking at a problem, if you're trying to come up with an equation, if you balance the units, a lot of times that's really all you need to do. And maybe you throw in a constant to kind of create a ratio, but it's very natural. It's very simple. Once you get the units to even out, everything falls into place very nicely. So, there's an app for that, and of course, it's an Eli app, and I called it Units. You can find it on my website, 2718productions.com, and it's kind of interesting. The icon of the app, when you sort of start thinking about what are you going to put for the icon, and I put MKS as the icon, and that stands for meter, kilogram, second, and those are the real base units that you're going to be seeing all the time. And usually we have English units like pound, foot, second, and a lot of times instead of saying SI units, you'll say, oh, are you doing MKS, or are you talking about, English units? Or American units at this point. We're like one of the only first world countries that hasn't adopted the metric system. It's kind of embarrassing. But anyway, different topic for a different time. So in the app, I kind of give you a list of 15 common units so that you kind of got to get a little familiar with them. And when you say, okay, what is my standard unit? When you have something like time, you say, okay, obviously the second. But when you get into, pressure, energy, power, and you're not really familiar with it, you got to kind of see it a few times before it really starts clicking in for you. So I'm just going to go through my list here. I got the app open. And for distance, we have the meter. Mass, kilogram. Time, we use the second. Force, like I said before, we use the Newton. For pressure, we use the Pascal. Energy, we use the joule. Power, the watt. Resistance, we use the ohm. Voltage, the volt. Current, ampere. Temperature, we use Celsius. Frequency, we use the hertz, which people usually call stuff per second. I'll get to that. I'll just finish this list here. Electric charge, the coulomb. Capacitance, we use the farad. And magnetic flux density, we use the Tesla. And a lot of those you'll find are named after famous scientists, like Tesla is named after Nikola Tesla, Newton, Isaac Newton, Ampere is named after Ampere, electric charge, Coulomb, named after Augustine de Coulomb, Farad is named after Michael Faraday. And so a lot of times what they'll do is when you have a new unit, somebody who usually pioneered the field, but a lot of times scientists, you like to give it up for your elders and the geniuses whose shoulders you're standing on to take it to the next level. And so they like to, even with the elements, they're starting to do that now. Well, they have been doing it for a long time. But they like to kind of, pay respect to people who they think have advanced science in a big way. Two of them I really want to mention. Celsius, if you're from Canada or anywhere else in the world other than America, you're probably familiar with it. But to Americans, converting between Fahrenheit and Celsius is like unbelievable. Like, you have no idea. If someone says, oh, it's 23 Celsius, you're like, I don't know, is it freezing? Is it boiling? Who knows? And how is this different from the SI unit, the Kelvin? Well, Kelvin is measured in reference to absolute zero, which is no energy. It's the coldest you can get. And from there, you go up. And the difference between Celsius and Kelvin is that 0 degrees Celsius is equal to 273 degrees Kelvin. So if you take your Kelvin temperature and you add 273, you got Celsius. I think it's like 273.15. But it's a good, rule of thumb, I guess you'd say. And then with Fahrenheit, you actually have a little bit more complicated. Convert from Celsius to Fahrenheit is like slightly more involved, I guess you'd say. But when you're doing thermodynamics, everything's got to be in Kelvin, and so that's really the one you want to go off of. But from day to day, you're talking about Celsius, and so we kind of keep it metric, as metric as possible. So that's a pretty good unit. And so from here, I have a tap review, so you can see this quantity, time, mass, distance, pressure. You tap the word, and it comes up and it tells you, and that's sort of like the next step in getting familiar with these units. And then to kind of cap it off, we have flashcards, and it'll ask you, okay, what is the standard unit for distance or length? Is the meter? You hit the answer button. Capacitance, the farad. Voltage, I know is the volt. And so you can kind of roll through those. That's free on the App Store, so check that out. I also have, if you don't have an iPhone, you silly goose, I have videos on YouTube that kind of roll through the same thing. It kind of gives like a formal introduction to what I'm talking about now. And then it goes through in video format those 15 units. It kind of gives you like a 5-second countdown. So check that out. I think that's pretty useful. And if you like it, let me know what you think. You can either leave a comment or drop me an email at pwnyourhw, pwnyourhw @gmail.com, or 2.718281828productions@gmail.com, or info@2718productions.com. Whatever tickles your fancy, I kind of check all those, so no problem. What else do I got for you today? So yeah, learn how to measure. It's important. You have to be specific about what you're talking about. And people who are good at it, man, if they can smell you from a mile away if you don't do good measurements, and they'll rip you apart. So get familiar with the units. Units got to balance out. And yeah, I think that's the next brick in the wall here in building a really cohesive idea of physics. So you got the Greek letters. We'll demystify a little bit there. We're going to do units. We did units this week. And then next, we're going to do prefixes or powers of 10. And how do we modify these units of measure when they don't exactly, when you're measuring something much smaller or much bigger. And so we'll get into that next week, a little preview. So yeah, brick by brick, guys, we're getting there. So I'm going to sign off. Tweet me, 2718productions. Check out the website, 2718productions.com. And subscribe on iTunes if you're into the whole iTunes thing. So I hope you're enjoying the podcasts. I'm going to keep them coming. Check out the YouTube channel. Check out the Twitter. And I'll catch you next time, guys. Take care.